Okay, in this lecture we're going to take a look at an introduction to normal distribution. So first of all, we're just going to talk about different types of data. So there's two types in general. There's qualitative and quantitative. Now, qualitative data is more about it's not numerical. It'd be like the color of someone's hair, the color of cars, stuff like this. So qualitative data we're not going to take a look at. We're now looking at quantitative data, which is data which can either be counted or measured. And we define both of these now. So continuous data is the type that's measured. So with continuous data, your values can take any value on a range of possible. So say if we're talking about the heights of adults, a person could be anywhere really from say 100 centimeters up to say 250 centimeters. So the data falls within a range, and to find continuous data we usually measure it with a measuring tape in this case. Then there's also discrete data, and discrete data is the type that only has whole number values. This is usually determined by counting number of cars sold, number of children in a household. So what we're looking at today really looks at continuous data. It's a measurement used to analyze continuous data, which as scientists we deal an awful lot with stuff we measure. So this type of analysis, normal distributions, is used an awful lot in science. So we're just going to take a look, go into the heights example. We're taking a look at 600,000 adults. And this is a histogram. It's like a bar chart, but it's a bit more sophisticated than a bar chart. But here we can see that if we take our 600,000 adults in intervals of 20 centimeters, this is how their heights play out. So now we can see there's a general there's most people fall into the middle, which is what you'd expect. And this really is the essence of normal distribution. But now what we'll do is we'll just change the interval sizes over the next few slides. And if we reduce the intervals to 10 centimeters, so now we get a bit more of a defined picture of the heights of these 600,000 adults. If we make the interval smaller again, to 5 centimeters, we get again a more detailed picture of the heights of the adults. Make the interval smaller again and smaller again, and essentially we see that this curve, this bell-shaped curve, develops. And that's kind of described as the normal distribution curve. But there's a few conditions attached. It's not just, oh, it looks like that, so it is. There's several conditions that are attached, and we'll look at those very shortly. But this is the type of thing. An awful lot of stuff falls into this normal distribution, bell-shaped curve. You've often heard it described as pattern. So just a few examples of where this occurs. We've seen the heights of adults forms this normal distribution curve. The weights of adults also produces that kind of curve. Shoe sizes, both male and female. Exam results. The leave insert is fitted to this bell-shaped curve. You often hear the minister always comes out at the time of exam results and talks about how everything is great and all, and it's like, well, it is great because you've fitted it to one of these curves. So the leave insert is a very good example of the results are tweaked to make sure that we have a certain amount of very good students, normal students, and then there's always poor students. Like, it's just the nature of things. But the normal distribution is used to achieve that balance. Obviously, it's a little bit more difficult at the moment. The weight of children at birth is a normal distribution. Stock market share, so the way stocks move and bought and sold on the open market, produces a bell-shaped curve. IQ is actually designed as a normal distribution, so it obviously falls into this category. Intelligence quotient is what it stands for. Rolling a dice, we saw this in probability. If we roll 2 dices, 7 is the most common result of rolling 2 dices, and then at the extremes lies rolling either 2 from 2 dice or 12 from 2 dice. So this pattern, this shape, is very common throughout both nature and the world in general. If we toss a coin, probability of heads from 16 coin tosses. Blood pressure falls into this. Milk production, volume of milk production from cows. So it's kind of it's everywhere. The length of carrots and cucumbers, the length of produce. So basically, I think I've proved the point. It's very common throughout the world. Now this is the function. So this is the function that produces that bell-shaped curve, and you can see it's pretty complex. Like we're not looking forward to working with this, and thankfully we don't have to. But this is the function that defines that curve. Now it looks very complex. There's our x value. That's the input. That's what we can change. But really the function is defined by 2 things. The standard deviation, that's sigma. I know you know your Greek letters. And then we have mu. So sigma is the standard deviation. I'll just write it up, it's easier. And mu is the mean. So really the curve is actually defined by these 2 parameters. The mean is the average value. And then the standard deviation is often called the spread. How much does any value deviate from the mean? It's the average deviation. Standard deviation is the average deviation from the mean. So if the standard deviation is quite big, say if we were looking at student results, and then this was 50, and students kind of, say a class was very closely, they were all of the same skill, so these would be all the students alphabetically A to Z. These would be their results. So the mean is the average value. The standard deviation is how much the average amount of how much each result deviates from this mean. So here we would have quite a low spread of results because most students are kind of falling fairly close to the mean. Whereas we could also have a different class. And here we can see the spread is much greater. So a deviation is this much. We kind of ask how far is a result from the mean. To get the standard deviation, we add all these values. We square them so that any negative values kind of disappear, and then we get the square root of our answer. But here the spread is low, standard deviation low, and here standard deviation is quite high. So that's what the standard deviation is. It's kind of how much does an average result vary from the mean. So those 2 parameters then define the shape of our bell-shaped curve. So different centers, and the center and spread depends on the mean and the standard deviation, and we'll explain this in a little bit. So this is what a typical curve looks like. If we change the mean is here, it's this value. So if the mean increases, then the whole curve moves to the right. If the mean decreases, then the whole curve moves to the left. It stays the same shape, it just slides to the left or right on the x-axis. That's what happens if we change the mean. If we change sigma, the standard deviation, that changes the spread. It might make the curve more pointy, or it might flatten out the curve either, depending on. So a flat curve has a lot of spread, and then a pointy curve has a low spread. The main thing is though is the area under all of these curves would be the same. It's just the shape is changed by the standard deviation. Don't worry about these too much. You'll always be given these values in the question, and then you can start to work through to find the required solutions. So here we just have two typical normal distributions. It's just to show this difference between spread and position. The blue distribution has a mean of 50 and a standard deviation of 10. The red distribution, we can see when the mean has moved, the mean is bigger, so it's shifted the curve to the right. But the standard deviation is lower, so that's what gives us this pointy curve. Now, this is an important concept, is if we go, so when we have our results, so say we had, we were looking at marks, we'll do an example in a minute, but if we go to one standard deviation from the mean, so say we were looking at this example here, 50 and a standard deviation of 10. Say we were looking at exam results, and we will do this very shortly. One standard deviation would be 40. That's one standard deviation below the mean. And 60 would be one standard deviation above the mean. If we add the amount of PEEP students, there would be 34% of the students below in one standard deviation below the mean and 34% above. So we say that there's 68% of students would fall within one standard deviation of the mean. If we go to two standard deviations from a mean, so here we're looking at a mark of 30 to 70. So now if we add all of those values, that's 95% of students. So 95% of students would fall within two standard deviations of the mean. And then if we go out further again to three standard deviations, that would encompass 99% of students. So we're going to see later when we're looking at our tables will actually stop at 3.5 below and 3.5 above. But that's coming in the next lecture. Don't worry about that just yet. But it's very important to remember these figures. 68% in one standard deviation, 95% in two standard deviations from the mean, and 99% in three standard deviations. And this is how manufacturers and stuff decide, how to make shoes, Do we want the kind of shoe to be available for everyone in the population, or do we really just kind of want to sell as many shoes as possible to the average person? And this is why it's quite difficult for people to get shoes or clothes that are either very small or very large, because manufacturers don't make them because there isn't enough of a market to justify the manufacturing costs. Now, we're just going to look at the formulas next. Don't freak out, we don't have to do this, but it's just to show where those results come from. Here we're one standard, here's the mean plus one standard deviation. Here it is minus one standard deviation. That's what gives us the 68% in the middle within one standard deviation. If we go to two standard deviations, either above the mean or below the mean, we get 95%. And if we go to three standard deviations above or below the mean, that encompasses 99.7. Generally people say kind of about 99. Because you don't want to round it up, because then it's 100%, and that's not true. So 99.5 what you would often see as well. So we're just going to take a look just in kind of maths. This is what I was trying to explain in couple of slides ago. In a maths exam taken by 100 students, the results are normally distributed with a mean of 50 marks and a standard deviation of 10. So this is our curve. Note the mean is in the middle. The curve is symmetrical. We'll talk about that in a little bit. So 68 students would have a score between 40 and 60. 95 students would have a score between 30 and 70. And 99 students would have scores between 20 and 80. And then there might be one student getting kind of, 86, 87, or scoring less than 20 either. And this is a rule, this is nearly like a rule of thumb. If a scenario is normally distributed, then this rule of thumb applies. So it kind of allows us give, rough estimations to things without having to do any of the heavy calculations suggested on the previous slides. So just 6 features of normal distributions. They're symmetric around their mean. So that means if we fold them over across the mean, the curve lies on itself. There's absolute symmetry. This is essential for when we're doing our analysis. The mean, median, and mode of a normal distribution are equal. The mean is the average. The median is if we laid all the students' results out in ascending order. The median is the middle value. And the mode is the most common result. So just a feature of these 3 values all lie at the same point, which often happens as well in real life. That's quite a common feature. The area under the total curve is equal to 1. This is back to probabilities again. Normal distributions are denser in the center and less dense in the tail. We've seen this. 68% of students lie in the middle bit. Normal distributions are defined by 2 parameters. The mean, sometimes it's written as mu, or sometimes it's written as x bar. We're going to use both, but I will generally just be sticking with mu. Standard deviation then is given by the symbol sigma. And then this is just what I was saying in the previous slide. 68.2% of the area of a normal distribution is within 1 standard deviation of the mean. This idea of counting from the mean by numbers of standard deviation is very important, and that's why I'm introducing it here. This, very quickly going back, just even here. This idea of here's the mean, this is 1 standard deviation above, this is 1 standard deviation below. This idea, or this concept, is the underpinning concept of all the analysis that we're going to be doing. So just kind of keep that in the back of your mind. It's the 6 features again. You'll be asked short questions on these in the quizzes, so just kind of make sure you're au fait with them. How good is the curve for real data? So we'll take a look at some practical example. So a ladies mini marathon. This is real data. This is taken from a real data set. 120 competitors. And the mean weight of the ladies is 127.8 pounds. The standard deviation, how much does each lady on average deviate from this mean, is 15.5 pounds. So now we know our mean, which is mu, and we know our standard deviation. So we can start to make some assumptions. Just using the examples I've looked at, we can start to make some assumptions about how many ladies would fall within 1 standard deviation, 2 standard deviations, and 3 standard deviations of this mean. So there's our mean. There's one standard deviation below. We've subtracted 15.5. And here's one standard deviation above. We've added 15.5. We've added 15.5, sorry. So what we would expect, just using the maths without kind of, without weighing the individual people again, we would expect about 82 runners would fall within this category just by maths. In reality, 79 runners fall within this. So it's not absolutely accurate, but it kind of the same rule of thumb applies across exam results, shoe sizes, loads and loads of different scenarios, some of them which I mentioned at the start of the lecture. Now we go to two standard deviations. There's two, so now we've subtracted. Two standard deviations would be minus 31. Remember, 15.5 by 2. And then if we go to two standard deviations above, we add 31 pounds to the mean. And we ask, well, mathematically, how many ladies would we expect to fall within two standard deviations of the mean? Well, 95%. 95% of 120 is 114 runners. When we actually look at the real data, 115 runners fall within two standard deviations of the mean. So it kind of shows that the model is valid. It kind of does hold water. If we go then to three standard deviations, 3 by 15.5 below, 3 by 15.5 above, that would be 46.5 below and above. 46.5, sorry, forgive me. So this would encompass, we would expect 99.7% of the runners, which would be 119.6. And in reality, all runners fall within three standard deviations of the mean. So just bringing this back to the idea of, say, shoe sizes or something, this is where manufacturers kind of have to make their decisions to decide, well, will we make runners for nearly everyone? Even though we're going to sell very few runners that are either very small or very big, or will we just make runners for the bulk of the population, 95% perhaps, and then they could just go to two standard deviations. Now, it means people who have very small feet or very large feet don't get to buy their product, but they are still servicing 95% of the market, but they wouldn't have all the expensive tooling costs associated with producing shoes for what are essentially very small markets. Now obviously there's niche suppliers who step in and fill these areas, but obviously they're working with a very limited market from the get-go. So that, guys, just kind of sums up the introduction to normal distributions. I've broken the lectures down into 3 lectures to try and just kind of make it a bit more manageable. There's quite a lot in it, so we leave it there, and then in the next lecture we look at how we avoid using that very complicated formula for doing our analysis. Because say if we want to take a look at, not everything, we don't want to do our analysis in that very limited 1 standard deviation from the mean, 2 standard deviations, or 3. That's the only information we have at the moment. We need something a lot more robust than that to help us do calculations, and we also want to avoid using that formula if at all possible. So in the next lecture we'll take a look at that. So thanks for listening, guys, and we will chat to you shortly.